Okay, next we're going to go over horizontal asymptotes, specifically finding the values of them. We'll talk about what they're approaching in a different example. We're just going to look for values of them. And in order to do this, the very first thing we're going to learn here is to write each polynomial function so the term of the highest degree is a factor. What the heck does that mean? Okay. Let's go with an easy example. Here's our polynomial p at x is equal to x squared plus 4x plus 1. What is the highest degree in this term, or this function? 2, right? We have our x to the power of 2. So what that means, they want that to become the factor. So in other words, they want us to common factor that value out of this equation. So as soon as I have the highest value, my x squared, I'm going to divide each of the terms by x squared. So now we have x squared on the outside, and we're left with inside the bracket 1 plus 4 over x plus 1 over x squared. That's it. We need to know how to do that to start. We're going to do another example of that, just doing that type of factoring. Then we're going to apply it to how we find a horizontal asymptote. Okay? Okay. Another example of this, giving us an example, q at x is 3x squared minus 4x plus 5. Same idea, write it so the highest degree is a factor. Well, again, we have the exact same highest degree. It is our x squared. And what we're going to do in this case is we're actually going to take the coefficient of the highest degree also. So because the coefficient in front of that highest degree is the number 3, we're going to take 3x squared out of each of these. And in this case, we'll get 3x squared on their outside, and inside we'll be left with 1 minus 4 over 3x plus 5 over 3x squared. Okay? That's it. This is a skill we need to have in order to find horizontal asymptotes, because we're going to start to apply an idea of infinite values. Okay? And when we do that, this will come in very, very handy. So, we have that skill. We're very good now. Let's see how we can apply this. Now, what we're going to be doing is we're going to be finding limits. And we're going to be finding limits as x approach. Well, sorry. That's not the terms they use. We're going to find the limit as x tends to positive infinity and as x tends to negative infinity. Okay? And we're going to talk about this, what this idea means. Okay? Now, let's say they got our first example here, determine the value of each of the following. They've given us our a of limit of x as it tends to positive infinity. Okay. 2x minus 3 divided by x plus 1. Okay. So, in order to do this, we need to take the degree of our highest, or the degree of our highest term, and make it the factor of both the top and the bottom of this question. So, the degree of the highest term is our x to the power of 1. Okay? So what we're going to do from here is we're going to take this value, and because there's a 2 attached to it, we're going to take 2x divided by 2x, negative 3 divided by 2x. That's the top of the fraction. The bottom of the fraction, our term, or our highest degree, is only just x. So we're going to take x divided by x. And positive 1 divided by x. Okay. Those are going to become our common terms. So our common terms outside the brackets are 2x. And we're going to be left with 1 minus 3 over 2x. We'll leave it like that. Don't be afraid to leave it in a fraction form. It'll work out fine. And we're going to get x1 plus 1 over x. Now, this is important. We can cancel our x's out. We're left with 2. 1 minus 3 over 2x divided by 1 plus x. 1 plus 1 over x. I took that x out. I want to always go into this with the most simplified version possible. Because remember, this was all equal to, technically we were finding the limit as x approached or tended to positive infinity. What we're going to be doing here is we're going to be plugging in the idea of positive infinity in for the x value. Okay? Now remember, positive infinity is an infinitely large number. It's massive. So, especially with what we're doing here, our fractions are technically having the number or the value of x underneath. Doesn't matter what number we have on top. Could be 10,000, could be 3. Doesn't really matter. If I put an infinitely large number on the bottom, when you divide by a very, 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 very big number, does anyone know what we start to get close to? What is it? 0. That's right. So if I take the number 1 and then I divide by something like this. Okay, do that. Sure. Wow. My calculator rounded. It gave me 0. Let's actually get something. Whoops. Let's get something a little better than that as an example. Okay. I get a number that's almost 0, and we can get closer and closer and closer and closer to 0. So I want you to think of this idea. What we're doing now, when we go to apply these limits, we get 2. And remember our old limit rules. That's a constant number, so we can keep that on the outside. This is a constant number, so it stays the same as it is also. Minus 2 over 2 times infinity, if it's x. Sorry, that should be a 3 on top. 2 times x. Well, x is infinity, so we have 3 divided by infinity. Whatever you multiply an infinite number by, it's still just going to be infinity. Divided by 1 plus 1 divided by infinity. Well, like we said here, where we had, if we were dividing by an infinite number, we're essentially ending up at a 0 value. So what we end up with is 2 times 1 minus 0 divided by 1 plus 0. Well, when we do that, 1 minus 0 is 1, times 2 is 2. 1 plus 0 is 1. Well, 2 over 1 is the number 2. So what we've found here is the value of this horizontal asymptote. And we're going to tie this together. Our horizontal asymptote is at a value, if we put up a graph, there we go. We have an imaginary line cutting through this at the number 2. Okay. We haven't talked about how it approaches this, but let's just say we have something where it's coming at it like maybe like this, and then the other one's coming at it like this. Okay. We know we're not touching that imaginary line there. And that was our goal here when finding out the limit, what our value of our horizontal asymptote would be.